everyone. In this video, I'm going to talk about predictive simulation and average predictive comparison in the context of logistic regression, right? And so in other words, what I'm going to talk about is how we find basically reasonable cases to make our comparisons to evaluate the substantive effects that are basically associated with our estimated logistic regression model, okay? And as we kind of saw, this is not trivial because the change in predicted probabilities for a one unit change in one predictor ultimately inherently depends on the values of all other predictors that are included in the model. Okay, in that sense, evaluating kind of the substantive effect size of a logistic model is a little bit more complicated than evaluating the substantive effect size of a basic linear regression. Okay, we saw some of those examples in the previous videos already, and in this video I'm going to talk a little bit more about how we can choose meaningful comparisons to make these predictive simulations, okay, and actually evaluate effect sizes. Okay, but before we get to that, I just want to kind of revisit different types of predictions that we can make in R based on our logistic regression that we estimated, okay? And we talked about this a little bit in our past Q&A sessions, as well as in the context of linear regression, but I just want to kind of go through those one more time to make sure that everyone is on the same page when I talk about different types of predictions based on our logistic regression model. Okay, and as we kind of go through these different types of predictions, keep in mind that we can kind of specify our logistic model as a kind of combination of a stochastic and a systematic component. Okay, the stochastic component is basically just the underlying probabilistic or the underlying probability distribution for our outcome that we observe, right? So yn, that's our dichotomous outcome variable that is either 0 or 1, right? And so based on the fact that this is dichotomous, either 0 or 1, we usually think of this as a Bernoulli trial. Remember, Bernoulli trial is just a simple coin flip with some success probability. The probability of observing a 1 rather than a 0, okay? We call this success probability pi n. Pi n in our case is, or pi n in general, is always ranges between 0 and 1. And again, it's the probability of observing a 1 rather than a 0 in our actual kind of realized outcome yn, okay? Now note that this probability, the success probability, is not equal across all individual observations, right? In fact, we have different changing observations depending on the covariates that are included in our model. And this is where our systematic component comes in, right? We're modeling this predictive, we're modeling the success probability, pi n, the probability of observing a 1 rather than a 0 on our y variable, as a function, as a linear combination of all of our predictors x times our coefficients beta, right? So beta prime xn is just the sum of the individual predictors times their respective coefficients, okay? And as we talked about in previous videos, we're not modeling this probability in a linear fashion, just like the linear probability model, but rather we're plugging this into our link function, which is in our case the logit or inverse logit function. This inverse logit function maps our linear predictor, beta prime xn, to the range of probabilities that we or the range of probabilities that we can have, which is between 0 and 1. Okay, so we compute beta prime xn, plug it in our link function, we get our probability of success for each individual observation, and then we have a Bernoulli trial. We basically flip a coin for each individual with that respective success probability, and then we get either a 0 or a 1, okay? That's the underlying data generating process, okay? And we're estimating a model, assuming that data generating process, and then we get our estimates for beta for our different predictors, okay? Now, after we have our model, and again, we're just looking here at the first model that we worked with in the videos or in previous videos. We're predicting vote for the Republican candidate in the 2000 US presidential election, just using one predictor, namely this ideological feeling thermometer. And suppose now we want to make predictions about voting behavior for a respondent who basically centers or places him or herself at the center of the scale, so at this feeling thermometer being equal to 50. Okay, if we want to make basic point predictions without uncertainty, okay, we can use the simple predict function. First, we have to specify a new data set for the kind of scenario that we want to predict. Okay, this is just basically a 1-by-1 tibble where this feeling thermometer is equal to 50. Again, this is basically just the covariate scenario for which we want to create predictions. Okay, and then we use our predict function with our model output M2A. If you go back 2 or 3 videos, you'll see exactly how we estimated this model. And as a new data set, we use our data set that we just created new to create this to compute this predicted probability for this specific scenario that we just defined. Okay. The point here is, and I wrongly said predicted probability because the point here is that this predict function does not give us a predicted probability in itself. As you can see, this value is minus 0.244, so it can't be a predicted probability, right? The point is that this value that we compute here using the predict function, that's just the linear component. That's just beta prime xn. And that's not bound between 0 and 1. That can go in theoretically from minus infinity to plus infinity, right? So just using predict, what we're getting is basically just beta prime xn for the x's for the x values that we specified in our new data frame, and the beta coefficients that we estimated in M2A. Okay, so we just get one basically linear predictor for beta prime xn that we then have to plug in to our link function to actually get a probability. Okay. If we want to directly compute this probability, so we could plug this number into our inverse logit to get a probability, or in predict, we can directly add the argument type equals response. If we add this argument type equals response, then the output is not this linear predictor, but is directly this linear predictor plugged into our link function to compute the probability, right? So in other words, if we add this argument type equals response, then what we're getting is not beta prime xn, what we're getting is this pi n. So the predicted probability based on our covariates, okay? And that predicted probability in our case here is 0.439, so around 44% probability to vote for the Republican candidate for a respondent who placed him or herself at the center of this ideological feeling thermometer. Okay, so obviously in statistics and in your own analysis, we don't just want to make predictions without uncertainty. Ultimately, statistics is about appreciating and communicating how uncertain you are about the inferences and estimates that you find. So in general, what we want to do is we want to make predictions with uncertainty, and the big advantage of our Bayesian framework is we can directly use our draws from the posterior distribution to kind of propagate the uncertainty, estimation uncertainty, and fundamental uncertainty in our predictions. Okay, and we talked about these different functions to draw from the posterior distribution, namely posterior linpred or linear prediction, posterior epred or the expected value of our outcome measure, and posterior predict. Okay, and so there's always a little bit confusion of what each one of those do, but it always helps to kind of think about linking that back to our actual stochastic and systematic component that are part of our data generating process for this dichotomous outcome that we're trying to predict. Okay, linear predictor or posterior linpred, as the name suggests, just computes the linear predictor for our new data, where we just have one observation, where ideology is equal to 50, right? But now, rather than just having one basically linear predictor for our point estimates, we now have a vector of linear predictors, basically for different draws from the posterior distribution of our actual coefficients. Okay, so remember when we basically use the default settings, we have 4,000 draws from our posterior distribution when we run stan_glm. And so basically now we have 4,000 draws with different coefficients, intercepts and slope coefficients. And so for each of those, we can basically plug in 50 for our feeling thermometer, and then we get a different linear predictor. Again, this is this green part, the combination of beta prime xn, okay? And so again, these linear predictors, they are not bound between 0 and 1. They're just a combination of the x's that we set and the betas. The only difference is now we have estimation uncertainty, so we have a lot of different betas which correspond to different draws from our posterior distribution, okay? So that's the linear predictor, posterior linpred. Now, if we want to compute the predicted probability, we could directly plug in these linear predictors into our link function, or we can directly use posterior_epred, which gives us basically the conditional expectation of our outcome measure. But keep in mind, the conditional expectation for a dichotomous measure is equal to the predicted probability. So essentially what posterior epred does is it gives us the probability of pi n if we plug in beta prime xn into our logit link function. So this now is ranging between 0 and 1. It's the predicted probability for each of those. For this scenario where ideology is equal to 50, the predicted probability of observing a 1 rather than a 0. But it's not just one value, just like here, where we just have a point estimate for our coefficients and just compute the one predicted probability. But again, we have 4,000 draws from our posterior distribution with 4,000 different values for beta 0 and beta 1. And so we can make 4,000 different predicted compute 4,000 different predicted probabilities, and the variation across those predicted probabilities comes from the estimation uncertainty, the uncertainty around our beta 0 and our beta 1. Okay, so that's the predicted probability. That's our pi n that we then plug into our, or that we then use to basically, as part of our Bernoulli trial. Okay. The last thing, if we want to make predictions about individual observations, these predictions about individual observations are of course not probabilities themselves, but they're actually draws from our Bernoulli trial, right? This means actually flipping our coin with the given success probability that we estimated for that specific case, right? And we can get those predictions using posterior_predict. What we're doing then now is basically going further up in our data generating process. We have our predicted probabilities for each of our parameter draws that were drawn from the posterior distribution. And so for each of those, we're now flipping a coin with that success probability, and we're just recording whether that coin lands on heads or lands on tail. And depending on that result, this output of posterior predict will then be 0 or 1, right? And this now takes into account not only the estimation uncertainty around our betas, right? Because we have different beta values here, basically, that lead to different predicted probabilities, but we actually have systematic uncertainty, stochastic uncertainty, because we're flipping a coin again and again and again, and it can, with a given probability, land on heads or land on tails, right? So what you'll see if you use posterior linpred and posterior epred is that every time you run this command again and again and again, with the same draws from the posterior distribution, you'll actually get the same values for the linear predictor as well as the predictive probability, which makes sense given, since the draws from the posterior distribution are held constant. This is not so for the predictions for individual observations using posterior_predict. Every time you run this command, you flip a coin for each of those individual observations with the respective draws from the posterior distribution and the resulting predicted probabilities, okay? So every time you run posterior predict, you'll get a different vector of zeros and ones, because you basically take into account this last step in our data generating process where we actually flip the coin with those respective predicted probabilities. Okay, so much about the different types of logistic regression predictions. I think I'm going to take a quick break here, and in the next video we'll kind of use those techniques to talk about different comparisons that we can make and different average predictive comparisons essentially. Okay.